something. Yes, Istvan, the floor is yours. Thank you.
Okay, hi everyone. My name is Istvan Hegedus from Hungary, and I came here today with a project that I've been working for very long now. This is called FPGATED, which is the re-implementation of the TED chip of the Commodore 264 series computers, which is, as you can see, the Commodore 16, 116, and plus 4. About myself, I'm living in Hungary, Budapest, and I have an MSc degree in information technology. And I'm a network design engineer working for an international company. And when I was a child in '85, I got my Commodore Plus 4, and I loved it. I loved to program it in assembly, because it had the built-in TED monitor. So I always wanted to be an IT guy, an engineer, computer engineer. The only problem was that I never had a floppy drive for this Plus 4. I always used tape drive, which made it a little bit difficult to program, but later, I managed to get the drive when it was already obsolete, but now I have floppy, of course. So my interest started at the university in FPGAs and digital computer architectures, and that's how I started this project, the FPGATED. The main goal objective of this project is to create a cycle-exact FPGA replacement for the MOS 8360 chip, which is the graphic chip of these computers. And it should work in all 264 series machines by replacing only the TED chip. So the idea was that I just remove the TED chip and replace it with this new chip, FPGA, and all the others like the CPU and the other integrated circuits in the machine will stay and work as it should. The solution should be not much wider and longer than the original, because it must fit in the case and on the motherboard. And all its pins should function fully. I mean here the analog connections also, because the TED chip has analog chroma and luma pins, so they should also work. And of course the audio, although that's digital. So due to this, it should provide a picture via the original RF modulator, via the RF cable or the video connector. And of course, its price, my main goal was that its price should be reasonable, because still you can buy TED chips, although they are more and more expensive now every day. But it should be reasonable. Some history. So how I started. One day my Commodore Plus 4 did not turn on, and I suspected it's the TED chip. And this is how the idea was born, that if I cannot purchase a new TED chip, then it would be great to replace it with an FPGA solution. Spoiler, the problem was not with the TED chip, but it kicked in this project, so I started to work on it. And first thing when we start a project like this is to investigate the internet, check the internet whether anyone has done it. And I was surprised that no one. I found the FPGA 64 project, which was interesting, and I learned a lot from this. And that's when I decided that I will create one for the TED also. I started with the Xilinx FPGAs because I knew them from the university, and used Verilog HDL instead of VHDL because I found it much more close to C language, and I could program in C language, and I like C language. So for me, Verilog was the best choice. So how to start a development like this? First of all, extensive information research on TED. Here are some resources that I used, like documents available on the internet, the hardware specification book, the TED preliminary datasheet. It was very useful. And even the TED patent I have found on the net, which describes some of the inner workings of the TED. I do believe it's not fully the implemented chip, but it had to understand some aspects of the chip. As you know, in Hungary, these kind of computers were very, very popular in the 80s and the beginning of the 90s. So it has a huge base of programmers. So I investigated these forums, searched these Hungarian programmer forums where they discussed all the internals and tricks of this computer, which was very useful. I collected out lots of comments and messages. I have a doc file collection of those from these programmers. I have done measurements on the real hardware also, used the Open Bench Logic Sniffer, which is a very cheap solution. And for this, it was just enough with 16 channels. And luckily, I have an oscilloscope, so I could done oscilloscope measurements also later. In addition, I have analyzed emulator codes. It is also very useful, and I managed to contact Bill Hurd too via the c128.com page, and ask him also about some inner workings. There was one Hungarian guy who helped a lot with the audio part, because I had no idea how the audio generator works and how could I implement it. And Levente Harsányi, he explained it so well with digital integrated circuits that I just had to write the code and it was working brilliant. So it was really a great help. So let's see how I started the development. I did not use that breadboard where I use the cables and connect components. I started with this Papilio 1 and later Papilio Pro FPGA development board, which you cannot see here. It's the board under the green one, the red board. And I created this TED wing for it, which has, as you can see, DRAM chip connections with a voltage level translator here in the middle. It has a VGA connector with a resistor network doing the digital to analog conversion. Of course, I needed to test it with software, so I decided to add the IEC bus connector. The idea came from the SD2 IEC project. I investigated that one too, so I managed to add it. And the PS2 keyboard RS232, although I never implemented the RS232 part, maybe one day. Then I started to write the code, the core in Verilog in 2015. I know it's long ago, almost 10 years ago, but really I started so long ago. And in 2016, end of March, it was already working in a way. Here on the screen, you can see that the first time I've seen a picture. It was garbage, but I managed to fix that. And by June 2016, the first public release was ready, and I shared it in Hackaday. This was advised to me by Bill Hurd. He told me to use Hackaday for this project. And although it was still not a drop-in replacement, it was very useful, and I liked it. I like to use it. On this picture, you can see a C64 also. And there is the open bench logic sniffer analyzer on it. Those cables are there. So it's not working. The prototype is working there. Later, I started to develop further a +4 core in it with the Papilio Pro's DRAM. So I had to write the DRAM controller. And I used the SPI flash for multiple kernel and basic ROMs, which are switchable. But this took a little bit too long time for me. So that's why the delay in the final product that I created. So let's see the drop-in replacement, because this is much more interesting. Here we can see the first version, which was a proof of concept from myself that it can work really in a real C64. And because I had to do the hand soldering, I've chosen a 2-layered PCB board with the Spartan 60 QFP 144, because this one you can easily solder. And the size of the resistors and capacitors are 805. So easily manageable, but still it's better to solder it under microscope. But I have hand soldered it completely. In this one, I have implemented CVBS, which is the chroma and luma signals, the analog chroma and luma signals. So when I installed it, yeah, you can see here the different parts. When I installed it, that time the RF modulator was already working. Now you can see here the components, not too many components. I did not want to make it too expensive, so I wanted to make it with as few components as possible. There is of course, the heart is the Spartan 6 FPGA, which is already today obsolete because Xilinx has moved to Spartan 7. There are bus switches with which I do the voltage level translation to between 5 volts and 3.3 volts. Luckily, not all signals need to be translated, because outputs, which are inputs from the motherboard point of view, they can stay on 3.3 low LVTTL level. So I just needed to translate the data bus, the keyboard lines, and some signals, I don't remember by heart, but IRQ probably, and some other signals. There is an SPI flash on it, which contains the code of the Spartan 6, but it has plenty of room for additional data storage. So I plan to use it to store kernel ROMs also. From the beginning, my idea was that I want to see RGB picture also via SCART RGB connection, sRGB. So I plan to add this VGA RGBS header, and by default it works with 15 kilohertz RGB. So if we connect it to a TV or a monitor with a SCART, then we can have an RGB connection and very sharp picture, much better quality than the original via the chroma and luma signals. Here is a photo how it looks like inside. It's still wide compared to the original integrated circuit. One thing I did not mention, the connection underneath. It's an SMD DIL connector, IC connector. Later, there will be a picture of it. I was afraid a little bit of it because it's not a cheap piece. But due to the size, I could not solve it with a through-hole IC socket. And this gave me a freedom on the top side, on the top signal layer. The next thing was to develop it even further, because I knew that the TQFP is not a solution in a two-layer board. And the main idea was that we need a 4 layers PCB where the top layer is the signal, inner layer is power and ground, and there is another signal layer on the bottom. I used here a BGA chip to have it even smaller, which is the Spartan 6 LX9 CSG225. And on this one, we still have the bus switches. In the meantime, one of the bus switch got obsolete also, so I had to replace it with another one, but luckily these are not difficult to replace with other vendors. And I decided to include HDMI because the Spartan 6 can support HDMI. It has a TMDS signal output, so why not to use it? And when I designed this board and built it, the HDMI part was not yet working. It was just a plan that in the future it will work. Due to this, I had to move the VGA RGBS header on the side. So the space on this board is heavily used, as you can see. It got slimmer, but a little bit longer than the original version 1.0. But it looks much better inside the PC, inside the motherboard, in the case. On this one has on the HDMI these resolutions 720 times 576/50 Hertz, or if we use it in NTSC mode, then the 48/60. And we have digital audio out on HDMI. This was important also, that if I want to connect it to a TV via HDMI, I want to get the sound via the same cable. Let's see the backside, which I mentioned. So this is that SMD IC socket. I put here the type. You can buy it on Mauser. It's Presidip. As you can see from the photo, it has the straight legs, and on the top they are bent 90 degrees. So I can solder it on the PCB, and it works really fine. One problem was that the C16, Commodore 16, has a very bad quality of integrated circuit socket for the TED. So that must be replaced because it's so bad quality you can hardly insert it. You can, but it's very difficult to insert. You need power, strong power to insert it. Then COVID came, and the chip shortage came, and the Xilinx has stopped the Spartan 6 just when I wanted to start the production, mass production. So A couple of years went again. I don't know how familiar you are with it, but during COVID and after COVID, it was almost impossible to purchase FPGAs. So I could not purchase the Spartan 7 or Spartan 6. Thus, I had to wait a little bit, and I could start to produce this version 3.0 in 2023. Although in the meantime, I was working on the code to move it to Spartan 7 because it's a little bit different than Spartan 6. There are, however, better solutions inside. The HDMI part is even easier to code. So I was ready with the code, but I did not have hardware. But by the end of 2023, November, I managed to get Spartan 7 ICs and got the board planned in Eagle, and I had it produced by JICPCB. They produced it, but I had to hand solder it. And I did not mention that with the previous version also. I have done all these solderings are hand soldered. I bought infra heater so I can solder BGA chips. And surprisingly, it is working really fine and quite easy to solder. A lot of people are afraid of BGA soldering, but it was working for the first time. What do we have here? A little bit improvement was that for HDMI, I have included the ESD protection. Here you can see that we have ESD diodes and also for the VGA connector, ESD diodes. But all the others are mainly the same. Spartan 7 needed one more LDO because it needs 2 core voltages. But otherwise, it's the same. It uses less power. Here it is how it looks like inside the C16. I use the C16. I have the +4 also, of course. But I use the C16 because there is plenty of room inside, so you can easily connect. And here on the photo, you can see that I have the HDMI connection and also the VGA connector. I have with this cable, I created an adapter for it. The JTAG is not needed in the final product. This is for me to program them. So let's see, the summary of the main feature. I don't want to go into deep details how it works inside because we don't have time for that, but you can read it on Hackaday, some specs. So what the final product or current version 3.0 is using is this Xilinx XC7S15 CSGA, and it has below 50% utilization, so there are plenty of room to add new features, and I'm planning to add more features. CVBS Chroma and Luma output to get picture via RF modulator. Chroma is created via direct digital synthesis, if any one of you know what that means. Luma creation is at the moment a secret. I don't want to reveal it because this was the most difficult part of it, because you can imagine that an FPGA, maximum voltage an FPGA can produce is 3.3 volts, and the Luma must go above 4 volts. So here I have a trick which later I will reveal, but not at the moment, because first I want to come out and make it available for others. And then later it will be released to public. RGB header is there still with switchable, software switchable between 15 kilohertz sRGB or 31 kilohertz VGA. Actually, it's 30 kilohertz. HDMI connector, the same as with the previous version. Digital audio output, and it works on flat TVs, and software switchable scanline effect I have added, because on the flat screens, for someone, maybe it looks a bit weird that it's too sharp. So with the scan doubler, built-in scan doubler, I could create the scanline effects. And in addition, I created 4 software selectable color translation tables for HDMI and VGA output or sRGB. Not for the Chroma Luma, those are built-in, but these ones, we can, via registers, we can switch them. And one of them is a custom color table that will be modifiable via registers. The flash, SPI flash, is accessible from the +4 side, so in the future, firmware upgrades are possible from the +4 or C16. So here is a photo, how it looks like on my Dell monitor, EFT, without scan lines, so it's quite sharp, as you can see. What are the future plans? Of course, my first priority is to start creating in batches production for sale. I need to investigate. I don't want to solder it myself because it's time consuming and difficult, but I want the JSC PCB to produce them or other companies, so I'm currently seeking for that. SID chip development should be easy, but so far I had no time to deal with it, but it should be easy to add a SID chip inside it. So having a SID card. Improving the TED core, although it's, I would say, 99% accurate. I have seen some glitches in some of the demos, very rare, which still I want to take a look and fix. The FPGATED configuration software I am currently developing, this will make it available to modify the registers, save the configuration to the SPI flash, so when we turn on, it will load it. And of course, the custom color table also. Thinking on some kind of copy protection in hardware, because I would like to avoid that Chinese people copy it and sell it. I want to use the SPI flash for additional kernel or basic ROMs. Although there is no RAM on it, there is some RAM, DRAM, no, static RAM inside the FPGA still. So I'm planning to use that. Here are some references where you can get more information on this project. Hegedus.io, this is the main page where I'm sharing always the progress, and the core is shared. The very low code of the TED chip is shared, so that is usable. But of course, you cannot use that to a drop-in replacement without some additional codes. GitHub TED core, yeah, I put it to GitHub. You can find it there. +4 implementation. This is if you have a Papilio Pro, you can build a TED wing and you can have a +4. And I know that the MIST FPGA team, they have used this core. So if you have a MIST FPGA, you meet with it. That is also based on my core. So that's it about the presentation. I don't know how much time I have. Do I have?
Let's go for some questions. Yes, Istvan, don't worry. Many thanks actually for the presentation. I was laughing when you mentioned during the COVID period that FPGA was impossible to find. I think because why was that? Because everyone was doing the same. Actually, nothing to do at home, so.
Yeah, probably.
So no, but There is a question in the chat actually from Francois. I think it relates to the not to the drop-in but to the first prototype, if I'm correct. And he's asking, on the Papilio, the FPGA emulates both TED and the rest of the machine. Is that for testing?
Sorry, I did not get. Sorry, can you repeat the question?
I will just read from the chat. So on the Papilio, the FPGA emulates both TED, and the rest of the machine for testing? Question mark. Or maybe François, you can formulate your question if you like.
Oh, sorry, I'm trying to find it in the chat, you said.
In the chat, yes.
Yeah, exactly. So it's not, of course, it's not just the core, because if there is the core only, the very low code of the core, that's only the TED chip, and the C16 has the CPU, it has other supporting chips, the PLA. So yes, the Papilio core has a 6502 core also. It was not written by me. I used the T65, and the PLA is very simple. So I added that, and there is the wrapping around it. So yes, the Papilio Pro has a C16, Commodore 16 inside, not the plus 4. But if you want the plus 4, then on GitHub you can find, because I have written that one too, the plus 4 core. So yes, it has more inside. But this chip, the drop-in replacement, has only the TED part, and all the logic that needs for it to connect it to the motherboard and talk to the other integrated circuits on the motherboard.
Okay, thank you. By the way, the version 2 and 3, they look so neat. I mean, design is super nice when you show that.
Yeah, I wanted to, if I switch to my phone, I can show you. Let's see. Can you see my screen?
Yes.
So I'm using now my phone. Here is my desk, and you can see that here is the C16 with the chip connected. I have the analog connection to a VGA connector here. I connected the VGA here to the Dell display and the HDMI also. Let's turn it on. This is now the digital display with the scanline effects. So the signal comes via HDMI and via registers. I can switch it. I have to cheat a little bit, because if I want to switch it to VGA, then I have to put 01 here to this register. I turned off scanline effect, and in the monitor, in the display, if I switch the input to VGA, and let's see, we should see, yeah, this is the analog VGA display. It's also good quality, but the HDMI is much better, of course. And if we want scanline effects here, then we have to type 03 here. And on the VGA, we have the scanline effect. I don't know whether you can see it on the screen, but
yeah, we can see. Yeah. Thank you.
And at the same time, if I turn on my old CRT, the analog connection is there. So what you can see here is the CVBS signal, the chroma luma. So at the same time, they can work together.
Nice. Okay. I see Travis has a question as well on the.
I do. First of all, this is great project. I've got a +4 with a bad TED, so I'll be your customer here. My question was about the joystick interface. I know a common failure mode on the TEDs is the latch on the joystick interface. Did that come out in your development, and why that's been a common failure mode?
Yeah, that is actually the keyboard latch which used to die in the original TED chip. And that renders not the keyboard, but the joystick interface to not operate. And that one is not, this chip is not affected by that one. The inner problem with that latch is well described on the +4 forums. In the +4 word forum, the guys, they have identified what is causing it, but it's mainly inside the MOS chip, a transistor in the latch transport.
Like a race condition of some kind? Or?
Yeah, actually, well, it dies because of the ESD. So I cannot explain now the exact problem, but this one, the TED is not affected. Well, I mean, this FPGA TED is not affected by that, definitely.
Great. Thank you.
Although I have not added ESD protection on those lines because those are coming out via diodes from the motherboard, but it's much more safe than the original one. Yeah.
So it's more ESD damage than a design limitation.
Yes.
In the originals, of course. Yeah.
Yes, and
okay.
One comment regarding the HDMI audio is going via the cable also. Of course, not on this display. That display doesn't have a speaker, but I have here a TV screen. I can show it there also. I don't know how much time do we have. Do we have time, or probably not, right?
Yeah. Well delayed.
So I don't show it now, but on that TV, the audio part is working also quite well.
Like a quarry for the +4.
I had some challenges with the HDMI audio, and it's because of the audio was by nature digital, which is coming out of the TED, and I had to sample it, you know. But normally when you sample an audio signal, first you have to have a low pass filter to filter the high frequencies. So I had some challenges there. I had to do oversampling and digital filtering before sampling, final sampling. That's just an interesting story.
Super nice project. Many thanks, Istvan. I see there was also a couple of comments from François in the chat, but you can read this then in the chat if you want to stop. Stop sharing. Good. Many thanks. I will stop the recording now.